question was, do you require cryogenics today, and will that always be the case? And in our case, for at least with our systems, the way we build the qubits, superconducting circuits, we run at these very cold temperatures, and so I would foresee that being the case for our type of qubits for the foreseeable future. You may get to higher temperature superconductors, et cetera, but they're still going to need to be cooled at some point. So you probably won't be seeing it in your cell phone, at least our approach, for a while.
The approach that I was not talking about is a photonic one, where it also has to be cryogenic due to the need for superconducting single photon detectors, but in contrast to the millikelvin temperatures that you heard about from my colleagues, that's more like 4 Kelvin, which is also very cold, but I like to joke that 4K is a lot closer to room temperature than 10 milli-K is to 4K, and that is true from a technical perspective. Obviously, it's deliberately facetious, but in that case, there's also no fundamental reason why you can't make semiconductor single photon detectors that do operate at room temperature. It's probably a multi-hundred million investment from an Intel or an IBM or someone like that, and at the moment there's no real market for that. It's quantum doesn't rate a mention in that market. It's mostly biologists doing 2-photon microscopy, but there are prospects for room temperature operation in the future.
Just want to complete that well, there are different technologies. There are different ways to build a quantum computer. The principles are the same. You need a qubit, you need some operation between them. So we just named, so we are similar to D-Wave, we are using this superconducting technology, and or Jeremy is using photonics. There are other options like trap ions. There are different ways, or like quantum dots. So for us, the reason is that we are operating at the low frequency, like micro regime. We need to go low temperature to observe the quantum effects. If it like the photonics can take off and can work, then it can be, we can have a room temperature processor. So that would be the advantage of that.
So it was observed by one of you that for a circa 100 qubit computer, digital quantum computer, you needed somewhere around 10,000 bits of error to succeed with the error correction. Is the relative quantity of error correction to bits linear or polynomial or exponential in the complexity of the computer that you're building?
So in an error-corrected large-scale digital machine, then that ratio is basically fixed.
Yeah, but that's a huge number. It's a one yeah.
10 to the 4.
Yeah, 10 to the 4 is.
So I saw a bullet point up there about cryptography, and I was just wondering, your perspectives on how cryptography evolves with quantum computing.
So I think that was my slide.
I had no text on my slides, so I'm innocent of having that bullet.
Well, it's good to discuss that because there are lots of discussion about the quantum computer will break the RSA cryptography, and there are many conferences around that. How to go beyond quantum. So we should have in mind that what we know is this Shor's algorithm that breaks, it does factoring good, it breaks RSA, but Shor's algorithm, we can run that algorithm when you have this millions of the qubit. That's kind of very futuristic. But yeah, there's a very active field of cryptography. The mathematician likes to solve hard problems, so they're thinking, okay, what if there is a quantum computer now? Let's go and break it. And there are different techniques of lattice-based cryptography techniques that seems to be immune to quantum attacks.
Yeah, I might just tag on to that. So last week I was invited to give a similar talk to the president, I won't get this title quite right, but the president's National Security Telecommunications something or other advisory committee. And so depending which side of there's sort of a wall there that you fall on, quantum cryptography could be a good thing, or it could be horrendous in that it has at least the potential to enable people to read all previous codes that have been encrypted. To our knowledge, and I would think the three of us would probably know, there are no machines that run Shor's algorithm on a practical basis today. We can simulate gates on our machine and won't go into the details, but you can kind of run our machine backwards and you can factor numbers with it, but they're minuscule compared to what people who really are doing that problem have done. We factored numbers up to about 32,000, And so very small, and I think when we get the 2,000 qubit machine running, we'll do it, and it'll be 100,000 or something like that, so not practical. Having said that, In-Q-Tel, whom some of you know, is an investor in our company. They're they're the investment arm of the intelligence community, so clearly there are potential applications there, and again, to our knowledge, and I would think we would know, there are no quantum machines that are in operation in the intelligence community doing those sorts of problems.
Just quickly tag on, just maybe for a helpful point of clarification, there's two distinct things. There's quantum communication, so securing communications using quantum mechanics, which is not what any of us have been talking about, and then the post-quantum cryptography, which is post a quantum computer. How do you go about doing cryptography? And I think Bo would have heard this as well when he was there. But in fact, it's out in the public domain. The NSA have directed people to stop using codes that will be rendered useless when we have a quantum computer, which I think means that the NSA doesn't have a quantum computer without our knowledge, right? Is that the logic?
To challenge you gentlemen with the same question that I brought up in an earlier panel. There was the discussion of the need for a sort of ecosystems of organizations to take you from where you all are to many more and broader applications. And so maybe each of you could challenge the audience for a research or practice or application question that you would like to see someone step up and challenge. And you can take it in whatever order.
Should we do it left to right, right to left, or in a quantum manner? And
okay, Bo, you're up.
Let's do it simultaneously. Okay. We'll superimpose our answers.
I've been watching other debates where nobody stops talking,
Exactly.
So
yeah. We're going to be different than those.
Yeah.
So in our case, we have this really different sort of hardware architecture. That's going to evolve kind of naturally, given the way we are. It's going to become more general purpose. There will be more connectivity between qubits over time. It will tend to become, I don't want to use the word universal in the same sense that you both would, but it will become more general, I suppose. So I think that's going to kind of develop a pace. But where we really need help, and the challenge really to the community, is we need more smart people thinking about how to map applications onto this really different architecture. And then we need another set of smart people thinking about software tools to enable other smart people to more easily map applications onto it. So from where I sit, those are sort of the two big challenges. And I'm encouraged, in the case of Lockheed, who is our first customer, they have a specific application in mind: software verification and validation. And so they're marching down that path, looking at optimization and machine learning as well. Our friends at Google, major potential application is machine learning of one kind or another. But Los Alamos, a broad multidisciplinary scientific laboratory, really is looking at a broad set of new potential applications of it. And we need to multiply that, by a factor of 10 or something. In the end, or 100 or some big number. In the end, what we need more than anything to prove at least this path is going to work is one application. One application that shows quantum supremacy or quantum advantage, and that actually works, and that people can either solve a problem that they couldn't otherwise solve or make some money solving a problem.
Can I follow up before we move to the other? What in general, what are the characteristics of a use case that qualify it? Now, right away, I think fitness landscape optimization, just based on my read of what you've said.
Yeah, so the immediate, the thing that jumps out to you is, I guess we're looking at different pictures, but on the picture we're looking at is the Alps or something. And so that is sort of the native problem that this solves. And so there are problems like that we believe, in the financial community, as you might expect. We've been working with unnamed investment banks and hedge funds to see if you could find an application that was worthwhile on this. We've worked with government and commercial entities to look at how might one optimize, whether it be placement of a constellation of satellites to cover the Earth best, and to hit high priority targets, but to traveling salesman problem sorts of things, logistics related problems. So those are sort of the most obvious ones, but having said that, I wouldn't be surprised that in probably 2 or 3 years, we may be able to have a bigger impact in the world of machine learning or deep learning because of the ability of this machine to do rapid sampling and create, in our case, quantum Boltzmann distributions, not real Boltzmann, but a sort of a representation of those. And so there may be a potential that we can help in that, but early days. So I'm sorry I don't have a better answer.
That's Jeremy?
Could you, sorry, just remind me?
Oh, so it's, if you were to challenge the sort of ecosystem as represented here on the kinds of problems or questions they could begin to address that would help you folks to close that gap.
Yeah, I think my answer actually is very similar to Bo's. You know, D-Wave have, I think, it's unarguable the most, you know, complete stack, as Bo elaborated, you know, from hardware up it goes. And I think Ali highlighted that, you know, in the large-scale universal digital thing, there's almost a disconnect between applications. You know, you've got quantum physicists working at the bottom, and you've got, you know, abstract, mathematically minded, you know, theoretical computer scientists, mathematicians working at the top. And I think we will get the early wins, and I know Google are working towards this. We'll get early wins by fitting applications to the hardware and vice versa. And that requires, you know, joining that stack up a lot more intimately and having individuals who understand that. And of course, implicit in that statement is that, you know, we really need to know what those problems are, right? And understand. I've been through this exercise with quantum chemists. We've done a lot of, you know, prototype quantum chemistry applications on our hardware. And it's a long process. You know, quantum physicists like myself sit down with quantum chemists. You both speak quantum mechanics, so that's a pretty good starting point, but it still takes dozens and dozens, if not hundreds of hours to understand what it really is that they're doing, what the hard parts of it is, how to deconstruct those things, and then how to fit them onto your hardware. So for me, that's, you know, the real problems that are out there I'm interested in.
Okay, very good. Ali?
Yeah, I think my last slide was kind of answering this question. I just want to emphasize on the part that, again, for the feedback we can get from the different sectors of the market, just doing some kind of R&D for their own need to see if this computer comes to the market, become available for use, then how it's going to impact their products. Or we commonly get this question that how much faster is this quantum computer? It really depends on when you think about the economic side of that, it really depends on who is going to use that and how much economical advantage comes. So maybe, I mean, one of you is interested to come and do a good study of like, oh, if you give me like I'm doing that kind of optimization, if I can do this like that much faster, like 1,000,000 times faster with this amount of dollar, then I'm going to buy your product. So that feedback is also one of the good feedbacks that help us to think more toward the product. Because right now it's like really this R&D labs are very, I mean, there are researchers working there, but there's still this gap to think about, connect that to the actual market. The actual market product is a need to be filled, and that's the part that you can help us.
A couple of provocatory question and a comment. So since you're trying to develop an ecosystem, so when can we SSH into it, and how much does it cost per hour? That would be the first question. And then for the killer app, this is kind of a joke, but not really. Like, have you considered gaming? Quantum gaming would be pretty cool. Like usually gaming is always the killer app.
Yes, the first part is probably aimed at me. So the list price of our computers is $15 million. Time Magazine on their, so it's a supercomputer class machine. Time Magazine said on the cover that they cost about 10 million, so that's sort of become the street price, if you will. But if you'd rather lease one, we can certainly do that as well. So we don't today have a formal cloud offering, nor do our friends at Google, nor Amazon, or any of the cloud services. I would expect you'd see that in the next year or two. And the reason for that, from my perspective today, is we could open the thing up, but by and large, you're going to have to program it in assembly language or machine language. And as a company with 150 people in it, we would get killed with how do you actually use it and do it and stuff. So we need to mature with, I think, open source help, the state of the software tools before we open it up. And my expectation is it'd be, I'll just make up a number, but a few $1,000s an hour or something like that. But remember, in each second, you get, with our machine at least, you get 10,000 solutions to a very complicated problem without adding or subtracting. So really quite a different, so in a very short period of time, you get a lot of complete solutions if you can map your problem onto it.
Okay, Jeremy?
We do have a quantum in the cloud setup that you can access for free. It's mostly for research purposes. So.
Something that it's close to the quantum supremacy, or is more of a toy experiment type of thing?
It's more of a toy experiment,
Okay.
yeah. But in terms of getting your hands on the hardware, it's,
develop the tools and stuff. It's already available.
yeah.
Okay, that's
and the upgrade is coming soon as that first chip goes to the British Science Museum shortly. We're upgrading to the latest and greatest, which is a lot closer to the quantum supremacy regime, actually.
Back in the days of massively parallel classical computers, I'm thinking of sort of the thinking machines class, and also vector machines like convex type architecture. The hope was that many large-scale problems could be massively parallelizable. But as it turned out, very few real-world practical problems could be parallelized to that extent, and they were all killed by the serial component. So I'm wondering if that same thing, will happen here, and if not, why not?
So I'm having survived some of those transitions of architectures from vector architectures to highly parallel to massively parallel. There are some real sort of comparisons that you can draw to this much different architecture, at least that we have, than what people are used to. And the reasons that some of those architectures failed over time was, I think, exactly what you point to, and that is that the algorithms were either hard to move on to those machines or impossible, or there wasn't the payback that people expected. And so that again, I think that just says what I've said here is that we need some real applications. We need people who think differently to be able to map applications onto it. And I do believe, however, in this case, that we will find applications where, whether it's quantum supremacy or merely a quantum advantage, pay off, and where people can either make money or solve problems that they couldn't otherwise solve. It's going to be a while, however. So again, back to the quest for smart people. The best person, arguably, who we have in thinking about how to map applications onto, I won't even call them algorithms, onto our machine, is a fellow who, PhD physics from Stanford, worked at Livermore, went to thinking machines, was porting applications onto a really different architecture than any of us were used to. Then worked at Cheryl Handler's company for a while, and then came to D-Wave. So his path has been sort of circuitous, but he's looked at a lot of different architectures, and he thinks differently than the rest of us do. And so we need, again, I think it's people like that. But we're gonna succeed or fail because we can get some applications running.
All right, so go ahead, Jeremy, and then Ali.
Add to that. I think in terms of quantum supremacy and quantum annealers between D-Wave and their customers, Lockheed, Los Alamos, Google, if those applications are out there, they'll find them. But I just want to highlight that in terms of the large-scale universal digital quantum computers, it's unequivocal that there are applications out there, as both Ali and I walked through. So they're absolutely there.
Okay. So should I just second the previous answers that, yeah, and the quantum annealer really, it's ideally you want to have all these qubits to be coupled to each other. It's like you have a general graph, so you can map any problem on that. But on the hardware, there are always limitations. So one of our jobs currently, we are working on the design of different architecture to make sure what are the strongest architecture, that gives the speed up that we want. So we have a set of criteria that, for example, the graph connectivity is our top priority when we design an architecture for this qubit. But then, as Jeremy mentioned, when you go to universal quantum computer, having just nearest neighbor interact, coupling is enough. Just run any arbitrary quantum algorithm.
Firstly, I take issue with the gentleman at the back who said that gaming is the way that we actually use all of this technology. Clearly, it's captions on pictures of cats. And but more seriously, one of the classic hard optimization problems that people have spent billions of hours of supercomputer time on is protein folding. And I'm just wondering how close we are to having a D-Wave machine that'll be able to deal with protein folding.
Yeah, I think we get back to the question of connectivity between our qubits. So there were some folks at Harvard, and one is now at NASA Ames, Alejandro, our friend, and they did some work on that 3 or 4 years ago with a smallish problem. There's another company, a startup called DNA-Seq in San Diego, who's doing similar things, but so far not very large molecules. Practically, to be able to use our machine for not industrial size molecules, but ones that at least would be interesting, I would guess we're 2 generations away, where we have to make big improvements in the connectivity between the qubits to be able to do it.